In a previous video, I had discussed the basics of reservoir operations, or the philosophy of reservoir operations. And I had discussed how it is that you can get water stored in your flood pool. Remember that if you have flooding that's occurring downstream and you have significant inflow coming in from upstream, you may not be able to pass enough inflow to keep the pool from rising, and if that occurs for a long enough period of time, you can rise to the top of your flood pool where a different set of operational criteria are going to kick in. Now, there is no standard definition for top of flood pool, but for purposes of this video, I just wanted for you to think about this as being the top of the spillway gates in the closed position. Now, not all spillways are going to be gated, but for this example, let's consider that we do have a gated spillway, and that the top of the flood pool is the top of the spillway gate in the closed position. What you're looking at here is a Tainer gate, and you can see right here, this is the pivot point for the Tainer gate, and this is the lifting mechanism. So as you lift the Tainer gate, you get a higher top of gate elevation. So what you're doing is you're creating more storage because you have a higher top of gate elevation, but you're increasing the release because now you have flow that's going underneath the gate. In this slide, you're looking at the back side or the downstream side of the spillway gate. In this case, you're looking at the upstream or the front side of the spillway gate. The reservoir in this case is low. You don't have any water that's up against the spillway gate. But again, think for this discussion that the top of this gate in its closed position is going to be the top of the flood pool. This is an image that was taken out of the Corps of Engineers EM 1110-2-3600, the Management of Water Control Systems. EM standing for Engineering Manual. This is the spillway gate in its closed position. And you can see that this is the top of the gate in its closed position. And again, we're thinking of the top of the gate as being the top of the flood pool, or the top of the gate in the closed position is the top of the flood pool. This is showing the gate in the fully open position, but remember that there are increments that this gate will move up before going to the fully open position. And with each increment that it moves up, you're getting a higher top of gate elevation, but you're also increasing the release that's flowing underneath the spillway gate. So what governs this type of operation, by the way, this operation is called an induced surcharge operation, and induce means to force, and surcharge means extra. So we're forcing extra storage by lifting up the gates. One of the misconceptions that I wanted to talk about is that sometimes you'll hear that when spillway gates were open that the reservoir operators stored a bunch of water and they were forced to dump all that water. But they're not really dumping a bunch of stored water. And that can be verified just by looking at what happens to the pool elevation as they're opening the gates. If the pool is still rising, it means that you're capturing a portion of the inflow and you're still providing benefits to the downstream area. So again, I think that there's a misconception out there that everything that's stored is now being dumped. But again, look at your pool elevation. If it's rising, it means that a portion of the inflow is being stored, and you are still providing benefits to the downstream area during this type of operation. So this operation is governed by curves, and what I'm showing here is what's called an induced surcharge envelope curve, and it's a single curve, which I'll explain in a little bit more detail. But I also wanted to point out that you could have a family of curves that relate the pool elevation to the inflow that's occurred over some period of time, normally just a few hours, and that will lead you to a required discharge. You may also have the pool elevation related to rate of rise that's occurred over a certain period of time, and again, that could lead you to that will lead you to a required discharge if you're using that type of curve. And in a future video, I'll go through the development of those curves. But for this video, I just wanted to focus on what's called the induced surcharge envelope curve. Now that's shown by this blue curve, and the definition of an induced surcharge envelope curve is the maximum elevation for a given release. You also plot the red curve which is going to be the top of gate elevation. And really that's just to verify that the maximum elevation that's specified by the blue curve is not higher than the top of gate elevation, because if it was, it means that I have water going over the top of my spillway gate. Now these are plotted on what's called the spillway rating curve. And if we look at the axis on this, we have reservoir elevation in feet. By the way, this image is also taken out of that Corps of Engineers engineering manual dealing with the management of water control systems. So your y-axis is elevation, your x-axis is discharge, and all of these intermediate curves that you see, those are gate openings in feet. And so you'd basically just read whatever elevation you're at, whatever gate opening you're at. So if you're at an elevation of 708 and you have a gate opening of 10 feet, looks like that's roughly 70, maybe a little bit greater than 70,000 cubic feet per second discharge that you'll get out of the spillway. So let's talk about the development of this induced surcharge envelope curve. Remember, it is a what's called the maximum elevation for a given release. That's the definition of that, and we'll talk about its development. So it's developed by 2 points. The first point is going to be your minimum release at the top of the flood pool. So here you can see that the top of the flood pool is elevation 701 in this figure, and you can see that you really don't have any required release. And that's that's very typical that you would find that. If you have a downstream regulating stage and you're above that regulating stage, then it is quite possible that you would be releasing zero until you're required to make a release by these curves. Or you may have a very small minimum release. So in this case, this example shows that it's either zero or some very small release at the top of the flood pool. The next point would be the elevation at which the gates are fully open. Now this curve is the rating with the gates fully open. So we need to figure out, where does my envelope curve intersect with this gates fully open curve. And there's a couple of considerations that you'll need to make. One would be a dam safety consideration. Based on events that you model, how high could the water possibly get. And so you want to work with your dam safety personnel on helping to determine that elevation. Some of the other considerations would be just the access to the spillway gates. Sometimes there's what's called the catwalk that leads you out to the controls for the spillway gate. And so you want to make sure that you're not cutting off access with too high of a pool elevation to where the catwalk would be flooded, and you can't get to the controls to fully open the gates. So that's another consideration. And finally, you also need to consider about what's happening upstream. We do tend to think about the flooding that's occurring downstream, but when you get to these high pool elevations, you also have to take into account the people who are living around the lake, and also the backwater impacts that can be created from a high pool elevation and how that's going to affect people upstream of the lake. So those are some of the considerations that need to be taken into account when making the determination on those 2 points. So if you were to just consider those 2 points, then you could connect these with a straight line, which is shown by the red dashed line. However, you can see that that is not the way that this curve was drawn. So what I want to do is just focus in on this point and explain why this curve has this shape. So instead of doing a straight line, what's typically done is that this line is drawn in such a way that it's going to have a steeper slope early on. And if we look at the axes, we can see that for a steeper slope, that any given change in elevation leads to a certain change in discharge. But if we have a steeper slope, that certain change in elevation is going to lead to less of a change in discharge than it would when we get out to these less frequent events. And less frequent events meaning higher pool elevation, more frequent events meaning lower pool elevation. So what they're trying to do is to extend the benefits further out for these more frequent events. However, one of the things that happens is that you do have to flatten this out a bit as you get to these less frequent events. And one thing that this acknowledges, and again I think that this is misunderstood, is that it should be expected that you're going to get decreased benefits as the event becomes more severe. That the attenuation that you get in the downstream areas, or the mitigation that you get in the downstream areas, is going to be less if this event gets to be severe, because now you're starting to have bigger jumps in the discharge with a certain change in elevation. So again, it's important to understand that. In a follow-up video, I'm going to go over the use, because right now we just talked about the development of the induced surcharge envelope curve. So in a follow-up video, I'm going to talk about the use of the curve, and also talk about what would happen if I wanted to make changes to the curve, or what are some of the considerations that would have to be taken into account. So thanks for watching this video. If you're interested in other videos on this topic or other water resources engineering topics, feel free to subscribe to the channel. Thanks for watching.